my own scheme.
Unmute works better.
I'm up and running now. All right. So that bad joke wasn't on the internet anyway, so that's good. Okay, so this is joint work with Micah, who's a PhD student here in Oxford, and she sat back there. She does very nice talks about this stuff, but you've got me today, sorry about that. So we're going to be talking about some no-go theorems, telling you when you can't combine monads in a certain way, which is using a thing called a distributive law, and this appeared at LIX this year. Okay, so I'm actually going to introduce a monad mainly so that I can draw some pictures just to explain something. So monad is a triple. On some category C, we have an endofunctor, which should be called T. That's a typo already. And then the unit and multiplication, natural transformation. And I'm going to draw them as pictures like this, just for a couple of slides. So if you're not comfortable with this string diagram notation, it's not going to be there for very long. We'll move on to something else. So this is a diagram in the endofunctor category, and it's a monoidal category with respect to just composing endofunctors. Okay, so that's some pictures introduced. And a monad is a thing satisfying these axioms. So you always get told this thing that a monad is a monoid in the endofunctor category, and it's really easy to see in pictures here that it just comes out as these nice unitality and associativity axioms. So again, this is just to get us comfortable with the pictures. Okay, so really, I'm going to talk occasionally slightly more generally, but what we're really interested in here is finite tree monads on set for the purposes of this talk. So pretty concrete stuff. And I'm going to introduce a few because we're going to need them later. So there is a monad called the exception monad. So you can think of it as taking some set X and extending it with some exceptional values. So if you think in terms of computer science, these are sort of different errors that have occurred during your computation. And a special case is this maybe monad. So the idea here is you extend with some dunno or diverged type value. So this is a sort of potentially failing computation. Familiar to Haskell programmers everywhere, there is a list monad, a multi-set monad, and a finite power set monad. I may just say power set from now on. If I do, just assume I've said finite every time. We won't care about the sort of full grown-up version. And also, we will mention the distribution monad, which was mentioned in Richard's talk this morning. And if you weren't here at 9 o'clock, why not? Because it was a really nice talk. So this is the same gadget that he was talking about. OK, and then we need a little bit more context about monads. So it turns out that it's the well-known thing. Every finite tree set monad comes from doing the free algebra construction for some algebraic theory. So you take your algebraic theory, form equivalence classes of terms, and that spews out a monad. And you get one for every one of these things and vice versa. So from this algebraic perspective, the exception monad, you can think of that as an algebraic theory that just has a bunch E constants added and nothing interesting going on. We can think of the list, multiset, and power set as the free monoid, free commutative monoid, and free idempotent commutative monoid, which fortunately are called joined semilattices to make life a little bit easier. So that's where those monads come from. And then D, you can think of as the free convex, or another word that's used is barycentric algebra monad, which are the algebras we saw earlier in Richard's talk again. OK, so if we're given some monads, can we compose them to form a new monad? So the idea is we have two endofunctors, so we can compose them one after the other. And does that automatically carry the structure of a monad? And it's well known that that isn't necessarily the case. So what would we want to do? Well, in terms of the unit, we want something of this type. And it's obvious we can just sort of take these two units for the two individual monads and glue them together, and we at least get something of the right type. We also want to form a multiplication. So we put things down, and in order to get things in the right order, we have to cross wires here. So if we invoke Spengler's principle for monoidal categories, then this sort of wire crossing is bad. We're not allowed to do this type of thing. We need special permission. So what we need is some sort of natural transformation delta. So that's these things that are going to turn out to be distributive laws to let us glue things together. But not any old delta will do. So we want to have a bit of a think about what delta should also require beyond being natural. OK. So if we try and sort of prove that this thing satisfies the unit and multiplication axioms, then we find that we require the following 4 equations, which I've described graphically. You don't really need to understand these things if it's not clear to you, but the basic idea is that you can drag the various components of the 2 monads over the wires for the other monad if you do things graphically. And the other thing to note is these diagrams are moderately complicated. So we've got a sort of triple iterated application of the monad functors here. So depending on how complicated your monad's functor action is, these actually get quite fiddly to prove, and we'll see some examples of that a little bit later. So there's effectively 5 things you need. You need to find yourself some delta that's natural, and then you need to check a bunch of things, which turns out to get fiddly. Okay, so why would we want to do such a thing is an obvious question. The answer is that obviously we want to be modular. If we're computer scientists or mathematicians, we like to be lazy and build complicated things out of simpler things. And there are various technical benefits as well. So if we have a monad, it comes associated with a couple of categories, one called the Kleisli category, which you can think of as encoding sort of computational computation with effect, where the effect's encoded in the structure of the monad, and also a category called the Eilenberg-Moore category, which captures the sort of algebraic behavior of the monad. And for a composite that we've built via a distributive law, we get a bunch of nice benefits. So we get nice functors going between the Eilenberg-Moore categories in one direction. We also get some nice functors going between the Kleisli categories. One of the monads lifts to the Eilenberg-Moore category of the other, and the other monad promotes to the Kleisli category of the other. So in summary, really, we get some nice relationships between the whole and the parts, which is kind of what you'd want, because otherwise it's a somewhat ad hoc combination of the 2 monads. OK. Ooh, did I click too much? Maybe I did, but we'll live with it. OK, so if we want to do this type of thing, so how do we proceed? Well, assuming we want to not just work it all out for ourselves, it turns out there's some nice things we can invoke. Some monads turn out to sort of distribute easily. So the exception monad and 2 other monads called the reader and writer, which we won't need later, but they're fairly simple and might be familiar to some people. They distribute over, well, at least in the set case, anything else, at least on one side, because this notion of distributing is an oriented thing. So distributing over from one side is not the same as the other, and it works at least one way. And there are some nice positive results that let us sort of churn out distributive laws if our monads are nice in certain senses. So there's a notion of a commutative monad, which we don't need the details for, and it turns out they distribute on one side over monads that are described by linear theories. So these are theories where all the algebraic equations, they don't lose or add variables from one side to the other. So they're linear in the variables. So something like list, for instance, is linear. But an axiom like idempotence, where you lose variables or they get copied and deleted over the equality, is not. OK, so these are nice. And they cover a few things, but maybe not as much as you might hope. You quickly find that combinations that you want aren't covered, and then you have to do it directly. So, for instance, we thought we had a distributive law in the office for D over D. Turned out to be wrong. So then what do you do when it turns out the sort of nice thing isn't correct? Then you've got to sort of dig around for something. And, well, is there anything else? You just don't know. You don't know when to stop. Is it a sort of fruitless search? So it'd be nice if there was something sort of bounding whether or not the thing was ever going to work out at all. Sometimes you can find a distributive law, but, well, you don't like the look of it. These things aren't unique. There can be multiple distributive laws for the same pair of monads, letting you combine them in different ways. So it'd be nice to know, if you find a distributive law that lets you glue things together, but it isn't sort of doing the job for you, whether there are other possibilities that might turn out to be better. And importantly, although I'm not going to name names, although I will explain later to people that are scared they're using broken stuff, there's rather a large number of errors in the literature, examples and theorems. So yeah, it's not easy to get this stuff right. You do have to be careful. OK. So, right, the next few slides are a slight reinvention of history. So We didn't really do things in the order I'm going to describe, but the order I describe makes us sound rational and systematic, so I'm going to describe it that way. It's also easier to follow, I think, the development if we do it this way rather than the slightly more ad hoc way we originally arrived at our results. Okay, so there's a classical result that there is no distributive law. So this is saying we can distribute probability over non-determinism in this way. So this is a distribution and power set monads that we saw earlier. And this appears, I think, in the appendix of a paper of Veracker and Winskell, and they credit it to the usual private communication from Gordon Plotkin. And a lot of people in the computer science community at least kind of know that probability and non-determinism don't really interact well, but I don't know how well people actually understand this result. So in the next couple of slides, we're actually going to look at how it's proved. And the reason we might want to look at this thing is that there aren't a lot of other ideas for finding negative results out there. So Gordon Plotkin's little counterexample has pretty much been the foundations of all the other sort of either individual no-go results or slightly general theorems about how to break things. So it's kind of a foundational thing. And I think the most general thing I'm aware of before our work was being able to replace this D with a somewhat arbitrary monad T satisfying some conditions, but they couldn't get rid of the dependence on the power set, for instance. So that, I think, is the most general thing I was aware of. OK, so how do we proceed? We assume for contradiction that we have an actual distributive law of the right type. And then we focus our attention on this little 4-element set X. And then, well, the cunning part is we pick ourselves a clever term in terms of a distribution of subsets of X. So this is the term here, just to help you read it, is a 50-50 probability distribution over the subset AB and the subset CD. So we're going to see that on the next few slides. OK, so the next step is we take the naturality square for our distributive law, our assumed distributive law, and we're going to chase it round for some good choices of functions f1. And they're basically designed to interact well with our clever term so that we can do various maneuvers. So details don't matter too much here, more the sort of form of the proof. So if I go quickly, you don't need to know what all these f's and things are later on. But the point is we pick a substitution. And then, because this mixture-forming operation is idempotent, so if you take half of A and half of A, that's the same thing as just getting A back, because it doesn't really matter which side you're on. Then, chasing around, we get down to here, and it turns out that our term has now ended up in a kind of a nice form. It's got this unit of the monad on the front. And there's actually an axiom we can then apply to move our way round here. And that axiom lets us deduce that the thing that is down here is of this form. So this is all kind of straightforward. We're just sort of doing some maneuvers and then doing break stuff. And obviously that depends on the actions of P and D, which is what makes generalizing this argument a little bit fiddly. But if you figure out what can have landed down here, it's stuff in this collection here. So basically sort of pairwise mixtures of certain of the variables that we started with. OK, next step. We define another substitution. It's very similar to the last one, so we won't belabor the details. And this time, we need idempotence of this mixing operation again. But if you've been really fussy, we also need that this subset forming operation is commutative in order for things to work out. And we need to be fussy like this in order to generalize later. So again, we end up with something of a nice form with this eta on the front, which means we can do the same thing as last time, and we get a form for the thing in this bottom right-hand corner. And then we scratch our heads a bit and figure out what can have come from up here. And again, we get pairwise mixtures of certain of the variables, but not the same combinations that we had when we chased the previous diagram. So if we combine the last two steps, then the thing that we're interested in now is constrained so that it's only going to be built out of these pointwise sort of Dirac distributions. There's no interesting mixtures in there. So we can think of this as a sort of upper bound on what this thing can contain in terms of distributions. OK, so we know the pattern by now. We start with our naturality square again. We pick, or let Gordon pick, another clever substitution. This time, we exploit the fact that this pair-forming operation is idempotent as well. So now we end up with something in terms of singletons, which, if you know the power set monad, these are basically invoking the unit again. So this is something involving the unit and one of the operations from the other thing. So we can use the other monad unit law, and we get something that we understand in this bottom right-hand corner. And this thing is a pairwise mixture. So then we want to think of what can. Ooh, that's not very reassuring. It's back, is it? Not back. OK, so in the meantime, hoping it will reappear. We're trying to figure out what does a person do under these circumstances.
We have this issue as well. I'm just gonna...
On and off again.
Yeah.
We've got computer scientists in the room.
Stefano, is he here?
Yeah, I normally lecture in here, but it doesn't do that to me normally. So yeah, it's a new one on me. Hey! So we've diagnosed the problem and it's yellow. But the good news is the solution is yellow, so he's cancelled himself out, so that's good. Oh, no, he hasn't. He has. Maybe my moving is the problem. Maybe I'm the problem.
That's actually the problem is that it thinks the computer is sleeping.
Ah, well, I'll hopefully do enough to keep it awake. OK, so where are we? I think I clicked. Yes. I'm not having much luck here, am I? Here we go. OK, so we were chasing around this square before that brief intermission. And again, we were trying to figure out what can have come from down here and landed on a pairwise mixture of two distinct variables. And if we think a bit about the action of this function down here, it turns out that it can't be one of these things made out of singleton distributions that we found before. So we've actually contradicted the assumption that the distributive law exists. So that's how this proof works. And actually, a passing observation is that we've actually shown a stronger result, that there's no distributive law of pointed endofunctors, so just preserving the units going dp to pd. And I don't know if Neil's around today, but Neil talked about games yesterday, and during his talk, a distributive law of this type appeared in terms of natural transformations. But nothing naughty was going on there, because it turns out the distributive law used in that talk is one that preserves just one but not both of the units. So it's like really close, but it's right on the safe side of the line. So it turns out these things are quite delicate, basically. Things can work until you add just one more property that you need to preserve. OK, so summary. What did we need? We needed some algebraic or equational properties, such as idempotence and commutativity. So just a bit of thought lets us isolate those things. Then we needed some sort of slightly more mysterious properties that made the inverse image part of the argument work. And it turns out that not all monads are very nice from this point of view. OK, so if we want to generalize these things, it's not too hard to sort of generalize what you require here. But generalizing this inverse image part, it's a real pain, it's fiddly, and even if you get something that you think works, you can't be very sure that you haven't mixed something, or that's how I felt. We originally worked sort of directly, and you were never very sure you were right at the end. It sort of wasn't very reassuring that you hadn't missed an assumption somewhere. So how do we make things sharper? And it turns out the way to go is to use algebra. That will come to our rescue. And I need to accelerate slightly. OK, so Maciej Pirog and Sam Staten sort of provided the sort of foundational thing that we need. So there's an idea of a composite theory for a pair of algebraic theories. So we're wanting to talk about pairs of monads. They've got connections with algebra, so we want a pair of theories. And it's a theory U that has a couple of nice properties. So every term in the theory is equal to the way to read this is it's a T thing with S things inside. So it's just of a certain shape. We've just written it as a substitution. But it's just a T thing with S things inside. And moreover, this thing is unique up to provability in S and T. The paper states it way more precisely than this, but this would take us astray into sort of fiddly technical details. So we're not going to go there. The intuition is that you can prove these things in S and T. And like the idea of a distributive law is an oriented notion, this is of course oriented as well, because if we'd required S things of T things, that would be a different thing to require. Okay, so why are we interested in these? So the same authors have a theory for a pair of set monads telling us that every distributive law induces a monad that's the free model monad for a composite theory of two algebraic theories, S and T, corresponding to the original monads. And the corollary we're really interested in is if there's no composite theory, then there's no distributive law. That's the plan here. Okay, so we've now got enough that I can kind of describe one of our theorems. That's kind of the idea, is to just give you a flavor of what these things look like. So we want monads that come from two algebraic theories, P and V, and they contain two binary terms. That's what this notation means here. So this is the variable sets on the left-hand side of the turnstile. We require that the P term is commutative, so we can flip the order of these variables and we get an inequality. We require that the P term is idempotent as well. That's what this axiom is saying. And we also require a sort of variable management property. So if P of 1, 2 is equal to some other term P prime, then that term can only contain the variables 1 and 2. So it can't have some extra stuff or lose stuff going the other way, depending on how you want to read the equality. Okay, and we also require some properties on V. So we require that V is idempotent, and we require two variable management properties here. So if we have a term that is equal to a bare variable, then it can only contain that bare variable. And if we have something equal to our V on 1 and 2, then it better contain at least one of the variables 1 and 2. So yeah, you might want to wonder how natural or how commonly these axioms are satisfied, but we'll get to that in a minute. Just for now, I just want to give a sort of flavor of the type of assumptions that we're dealing with. And under those circumstances, there's no composite theory of P and V, and therefore no distributive law for the two monads. Okay, so some examples. We recover the original classic that there is no distributive law distributing probability over non-determinism in this direction. We also recover a result of Bartek, Klin, and Julian Salamanca that the double power set doesn't distribute over itself. Their result's actually worth highlighting because it turns out power set to the n for any n greater than 1 doesn't carry the structure of a monad at all. So that's a much stronger result than simply not having a distributive law. So it's quite a nice result, that. In addition, we get some new results. We get that there's no distributive law where you do probability and non-determinism the other way around. This was actually claimed before in a PhD thesis, but without proof, which I think means their external examiner was nicer than mine, and mine was very nice. And there's no distributive law doing sort of double probability. So the thing that we thought we had earlier that didn't work, it turns out we were wasting our time and there was no such possible thing. You cannot distribute the distribution monad over itself. Okay, and then that's a sort of simplest version of our work. It's the easiest one to explain. And in this same direction, we can not eliminate this commutativity assumption, but you can trade it off versus some of the other assumptions to get further no-go results. And they also kill off sort of natural-ish combinations of monads, so there are examples in which they apply. And we can also get rid of this somewhat arbitrary restriction to binary terms, so you can require more complicated terms as well, and that works out. Okay, so that was kind of the easy stuff. I'm only going to skim over the harder stuff because I'm going to run out of time in about 40 seconds. But really where we started, in fact, is we found a sort of just a single counterexample showing that list didn't distribute over itself. That's kind of the thing that made us think we should play around here, along with the fact that we didn't know what was going on with d squared. So in that direction, we actually kind of have a new technique. So this doesn't really come from Plotkin's original method. It's harder to explain because it's more complicated. It makes non-trivial substitution. So in the Plotkin argument, we're only ever really substituting variables for more variables. To prove these more complicated theorems, you have to substitute non-trivial terms for variables. So it's a more complicated argument, but it turns out various things then fall out. A thing that we call the too many constants no-go theorem. So basically, if you've got lots of constants around and there's a couple of other assumptions applying, then your monads aren't going to distribute over each other. We have a times over plus theorem, which is really sort of a bounding result, telling you conditions under which your distributive law must come from an algebraic equation of this form, which is kind of a classic one that crops up in the literature. And then we have some no-go theorems, which tell us if this doesn't hold in a suitably precise sense that we won't bother the details with now, then you get a no-go theorem telling that you can't distribute monads of certain forms over each other. And also a similar one where we have unitality and we have certain sorts of non-commutative trees. So in each case, these ones actually apply to sort of monads that we cared about. Okay, so some examples. The general theorems recover the fact that list doesn't distribute over itself at all, which was an open question. Although it does turn out that if you take non-empty list, it distributes over itself. And in fact, non-empty list distributes over list. And in fact, the maybe monad we mentioned earlier, that distributes over everything. So you can actually put a monad structure on list composed with list, but it doesn't come from a distributive law. And actually, this argument was pointed out to us by Bartek. So this one, again, it's subtle. In the case of power set, that doesn't distribute over itself. It turns out it's got no monad structure at all. And this is kind of the reverse situation in which there is a monad structure, but no distributive law. It turns out there's no distributive law distributing list over exceptions in this direction. So this is the reverse of the side on which exceptions does distribute. So the other way around, it doesn't work out. So as a single example, this is maybe not hugely exciting, but this is an example from the literature. And when you trace it through, it comes from a theorem in a paper, and the theorem is broken. And the way we spotted this one is via our too many constants theorem. But there's a direct argument as well that you can show that this doesn't work out. Okay. There's also a distributive law for the multiset monad over itself. So this is because the multiset monad is both commutative and comes from a linear algebraic theory. So you can use this standard result to get a distributive law between the multiset monad and itself. And it turns out from the times over plus theorem that there's only one possibility. So if you don't like that one, you're stuffed because there aren't any more, so it's not worth going looking. And just to kind of fill in one of the remaining combinations, there's a known distributive law letting you take multiset over power set. So this is again using one of these general purpose theorems. And the remaining case fails. You can't do it the other way around. I'm there in about a minute, I think. Okay. Yeah. Apparently this has to say summary, so I apologize. It says conclusions and further work instead, so please tolerate that. So summarizing, obviously we can produce these sort of general purpose theorems. I'll work as a sort of proof witness to that. The take-home message, this is the one I want to hammer in my remaining rambling along. These things don't routinely work. So we all know the sort of meta principle for category theory. Once you've found something that's type checks, it's bound to work. Of course, we all go and check these things. It turns out it's more the other way around. At least if you take a sort of sensible family of monads that crop up in the literature, it's almost more of them don't distribute over each other than do, which is a surprise to me. I didn't expect that when we started the work. In terms of how our proofs work, they all use axioms of this form. So some term potentially complicated with just x's appearing in it reduces to just a bare variable. So these kind of let you sort of strip off complicated stuff and just get down to bare variables. And so two examples of this are idempotence and unitality for list type structures. And other combinations where you sort of mix and match yield further no-go theorems, which are in work beyond the Licks paper. But one thing we don't know the answer to at the moment, although I'd be surprised if the answer is yes, is is this the only way to break things? It'd seem odd if it was. And currently what we're doing is generalizing beyond set. And the way that we're going is looking at more general notions of algebra. where there's enrichment and weird arities and things involved, which I think might be the subject of the next talk, so I'll stop.
So there's about 3 questions I'd like to ask you, and I'm sure other people too, but we really...
Okay, I'll run away.
A really quick one while Christian comes up and gets set up. Christian, you hear something? Come and get started. Any really quick questions?
Do you want to take me apart?
Yeah.
You're not going to do questions.
I can.
Or are you?
A quick one from
Yeah, sure.
Why you said this condition of absence of bias, which that seems to involve only one.
Yes, it's property on one of the things.
I'm Christian. I'm working with John Baez at UC Riverside, and I'm going to tell you about our new paper about enriched Lawvere theories for operational semantics. I'm going to make sure that we all understand what that means. And yeah, thank you for having me. This is a great conference. So a guiding question in computer science as well as mathematics and logic is how can we best integrate the syntax and semantics of formal languages. So the syntax meaning the formal grammar by which you construct terms in a language, and semantics meaning how you actually reify some language and recognize it in a concrete mathematical structure. So a very clear and simple answer from category theory is with Lawvere theories. It's a special kind of category. And you can realize that theory by modeling it by product-preserving functors in some category with finite products. So we're going to talk more about that. The question that our paper is addressing is how do we incorporate computation into these theories? And so a simple answer would be from basically a 2-categorical perspective. So when a computer scientist sees a category, essentially they see the objects as types and the morphisms as terms. And so if you want a higher level notion of rewriting one term into another, you need something like a 2 morphism. That's the whole idea. These could be representing rewriting. From a logical perspective, they could represent entailments, or it could just represent order on the terms. So here's the generalization that we're talking about. In a normal algebraic theory, the only relations are equations. So here we would have an associativity equation in the theory of a monoid. And roughly, so there might be some debate about the use of this terminology, but this is what we would call denotational semantics in computer science, where you've passed to the realm where computation is already complete and equality is already completely decided. Whereas in an enriched theory, you have a way of actually representing the process of computation within the theory. So here we would actually represent the associator as an actual 2-dimensional rewrite from one string diagram to another. And so computer scientists would call this operational semantics because it's still explicitly representing this, the operational aspect of the theory. So just to spell this out, so a Lawvere theory is essentially the idea of a Lawvere theory is that we're abstracting algebra away from sets. So classical algebra would have said that a monoid is a set equipped with a binary and a nullary operation such that it's associative and unital. And nowadays we see hybrid structures everywhere, and we just want to say that a monoid is something equipped with a binary and nullary operation with the same axioms. And so that's what Lawvere theories do, is that they abstract away the idea of a monoid, or as John likes to say, the Platonic ideal of a monoid. And we have this category where we essentially just have this one central object that will eventually be like the carrier of our structure. And then all the other objects of the category are just finite powers of that object. And then morphisms from an n-fold product back to the object are n-ary operations. And that's all you need to specify by universal property of products. And then you can specify equations by commutative diagrams. So this is a sketch, and then you form the free category of finite products on this sketch. And now you have this category such that when you have a product-preserving functor from this category, it amounts to picking out a specific set, for example, for this M, and then it sends, because it preserves products, it sends this binary operation to an actual binary operation on the set, and similarly picking out an element for the identity, such that the equations are preserved. So the generalization that we're talking about is that we're replacing these equations with two-dimensional rewrites. So this is the theory of a pseudo-monoid. So there's a lot of talk about monoidal categories in this conference, and you will be relieved to know that there's a theory of monoidal categories. So it's exactly the same, except we might choose to write the operation as tensor and the monoidal unit. And now we have these two-dimensional morphisms, and we're going to talk about how we're doing this later, such that these fulfill their own equations within the HOMs. So the idea of this enrichment is that we're equipping HOMs with more structure. You don't just have to have a set of morphisms, and you can have as much structure as you want between them. So, so an enriched category. So it's a really interesting and important generalization of a category. And arguably, one day we might introduce category theory this way, because often HOMs have more structure than sets. It's kind of only in the category of sets where the HOMs are only just plain old sets. So, so when you define a category, it consists of composition and identities. And all you really need to define that is some associative tensor as well as some monoidal unit in order to do composition and identity. So we can do this on much greater generality than relying on this being Cartesian product of sets in the terminal object. So we let V be an arbitrary monoidal category. And then a V-enriched category has HOMs which are objects in V rather than sets. So that you could have HOM vector spaces, topological spaces, or groups, or anything. And then all the other definitions are exactly the same as for a normal category and the two category of categories, except now everything needs to respect the structure of V. So if this is a HOM graph and this is a HOM graph, then this composition operation needs to be a graph homomorphism. It's not just an arbitrary function. And similarly, everything else needs to just be respecting the structure which defines the category V. So in the same way that we get a two category of categories, we get a two category of V categories, V functors, and V natural transformations. If I ever forget to say V, it's all just V. So for our purposes, we're letting V be a Cartesian closed category because that's where computer scientists spend a lot of their time. If you see people writing in Haskell, what Cartesian closed means is that you have this product HOM adjunction. And so if you see people writing functions where they just have like a sequence of arrows for the input arguments of a function, they're implicitly using this currying equivalence. And also this closure gives you the fact that V is enriched in itself, which is a very interesting situation because you can use the internal HOM as its own HOM morphism. And then for some technical reasons, there's a very interesting generalization that happens in enriched theories where you can talk about arities that are not just natural numbers. And there's surprisingly little literature about this, and it seems like a very powerful generalization. And unfortunately, I don't have time to get into it. But basically, in our paper, we say we don't care about that generalization right now. We just want to focus on normal theories with natural number arities. And so the way we have to do that is that we need to find something that's essentially like the natural numbers hiding inside our enriching category. And we can just take finite sums of the terminal object, so finite discrete graphs, discrete categories, et cetera. So we just stipulate that as one more extra condition. Most categories we care about are going to have that. And then for purely bureaucratic reasons, we label this as our arity category. So similarly, since Lawvere theories are all about products, what we're going to call V theories are all about V products. And so the definition is exactly the same as normal products, except everything needs to respect the structure of V. So Hamming into a product is the same as the product of the Hams into the component objects. And similarly, for what it means to preserve V products is exactly the same, except now this is a V natural isomorphism rather than a natural isomorphism. Also, if you have any burning questions, just feel free to. And so we're going to denote VCat FP to be the sub 2 category of all the stuff that cares about finite V products. So now we get to the object of study. We are calling it a V theory. And essentially, in the same way that a Lawvere theory is just a category with some object where all the other objects are finite products of it, a V theory is just a V category whose objects are finite V products of a distinguished object. And we're going to call it T. And of course, these form a sub 2 category of V categories with finite products. So naturally, where we model them are V categories with finite products. So it's all exactly the same as normal Lawvere theories. So we're going to call this a context C, and then a model is a V functor that preserves finite V products, and these form the category of models. And as long as V is nice enough, if V is complete, or actually I think you only need equalizers, then this is actually better than a category, and it's itself an enriched, it's a V category. So if you're familiar with how Lawvere theories give you monads, you can actually get an enriched monad from these enriched theories, as long as your V is nice enough. So just to revisit this example, we're enriching in categories. And so here, these are distinguished like generating 2 morphisms. And when we want to specify these equations, we're just thinking about going inside the cross-section in this Ham from m cubed to m, and we're drawing a diagram. If you've seen this pentagon equation for the 2 ways that you can reassociate multiplying 4 things. I'm not sure I have time to draw it, but that's what it's doing. Does this good? All right. So something that might be of interest to category theorists is that you can do more than just weakening equations to something like equivalences. You could actually, now that your Hams have more structure, so a V theory for V being cat is essentially a 2 category with finite 2 products. And so it would make sense to talk about things like the theory of categories with finite products. And this is kind of one of these meta microcosm principle situations. So here we could have a binary and nullary operation and actually specify that they have adjoints, because we're in a 2 category now. So this is kind of a testament to the power of the generalization of enrichment, is that now all Lawvere theories are models of a particular enriched theory. So here, one of the applications of this generalized arity is that limit and colimit are actually operations that have a arity whose shape, which is the shape of the diagram. So here you could so-called power by certain shapes of classes of limits or colimits, and you could actually have a theory of categories with certain kinds of limits or colimits and generate a 2 monad for those kinds of categories. But that's getting away from the main message. So the original idea of our paper is that the choice of enrichment should be some kind of method of reasoning about your theory, or way of computing in your theory. And so our idea is that a functor between enriching categories induces a 2 functor between the 2 categories of enriched categories. And we want to be able to think of that change of base as a change in the way you're thinking about your theory. So for example, here, we could start with enriching in graph, and this would be some theory where you can only see 1 rewrite at a time. And this would be so-called small step operational semantics. And you could, on the HOMs, you could take the free category. So this would be allowing you to travel along finite sequences of rewrites. And this would be passing from small step to big step operational semantics. And then you could go further and only care about the existence of a rewrite from one term to another. And this would be taking the free poset on a category. And then finally, you could only care about connected components. And you can quotient by connected components and equate any term with everything in its future or past. So this is the motivating. This is the motivating example. But what we're proving in general is that is conditions for changes of base to be thought of as a change in theory and change in model. There's just one technicality here that we need to correct on the archive, is that the free category functor actually does not preserve products for a simple kind of funny reason. And we need to replace it with one-dimensional simplicial sets and figure out how to write the paper without scaring people about simplicial sets. All right. So, So change of base, if you have a functor between enriching categories, so preserving finite products, and you have some V category C, you can transform it into a W category by just, it still has the same objects, but on every HOM you're just applying this functor. So you're sweeping to a new kind of structure on the HOMs. And so this induces a 2 functor from all V categories to all W categories. And so, as we were saying, if enrichment is a choice in like a method of reasoning about your theory, then a change of base should be a change in that method. So the result of the paper is that you actually don't really need to assume hardly anything at all. So actually, pretty much any functor that preserves finite products, and then you also need to preserve these arities, can be considered as a change of method, in the sense that there's a canonical way, if you have a V theory, and this is the bureaucracy about how to define a V theory, there's a canonical way to get a W theory, and similarly, if you have a model of a V theory, there's this, the image in the change of base is a W theory. So I said a Cartesian closed functor, but you don't even need the closure. If you want to say nice stuff about enrichment and monads, then you might want the closure condition. But the main message is that we can think about finite product preserving functors as changes of method. And then the example that we chose to demonstrate these ideas is the SKI combinator calculus. There's this really interesting subject called combinatory logic that was motivated by the subtleties of variable binding in the lambda calculus in like the early 1900s, beginning of modern logic. So the SKI calculus is basically a variable-free version of the lambda calculus. You can compile down lambda terms into big trees of SKI and these applications. And basically these combinators imitate 3 basic things that can happen under a lambda abstraction. And so we chose it because it's a very simple example of something that you really want to enrich. There are no equations in this theory. Nothing is even close to associative or anything. And you have these rewrites where if the S combinator is applied to 3 things, it applies the first to the third and then the second to the third. You have these rewrites. So here we could start out imagining that we're enriching in graph, and these are distinguished HOM edges. And then we can do this spectrum thing where we go through the different levels of semantics by which we could analyze this theory. How am I on time? Okay.
5 minutes to go before
Okay.
your 5 minutes of questions.
Yep. Thanks. So, and then we just demonstrate how in an enriched theory you are actually, when you model this theory as a graph theory, you actually do get the graph of all terms and rewrites in the SKI calculus. So here you have some mu from the theory into graph, and it's going to pick out this graph mu of t. And so the the combinators were null area operations, and now they're becoming distinguished vertices in this graph. And then, because it preserves products, you're getting a binary operation on the graph, which is actually a graph homomorphism. So that's how you're going to like carry these rewrites into a way of actually like S blank blank blank. So for example, if you plug in something here, K of some vertex blank, that'll be a graph homomorphism that faithfully represents the rewrites. Yeah, sorry, that would deserve some drawing, but yeah, this is the idea: is that the enrichment will do what you expect and give you the actual structure of the terms and rewrites in the theory. And then if you're wondering, okay, well, there's this space of all these strange models, but usually you just care about the graph of all closed terms and rewrites in the SKI calculus. There's this idea of taking the free model on a theory. It's a very important idea in algebra. And here it would just be the representable out of the terminal object of the theory. So this is just taking the free model on the empty graph rather than imposing more structure from the beginning. And we just show that it's giving you the small step operational semantics of the theory. All right, and so we perform this spectrum of method of reasoning idea. So here in the black we have these Hom edges representing rewrites. So this would be the initial configuration or the initial enrichment. And then if we take the free category, so we were really doing it on simplicial sets, then we're joining all possible composites. And then if you take the free poset, we are collapsing this to the Hasse diagram that just doesn't care about the different paths, but just asserts the existence of paths. And then finally, since these were all kind of a part of the same computational process, this connected component would all just collapse to a single point. So yeah, it's just giving you, this is just one example of this change in reasoning, and it's just giving you a spectrum, in this case, yeah, this spectrum of level of detail of analyzing the theory. So yes, in conclusion, enriched theories give a way to unify the structure and behavior of formal languages. That's the new aspect. Okay, first of all, this is not new. This is so the idea of enriched theories is like giving you this. This general idea has actually been known for quite a while, but it hasn't gained sufficient popularity, I guess. So to me, it seems like there's a ton you could do in computer science with enriched Lawvere theories, but there just hasn't been much about them yet. The new thing about our paper is just interpreting change of base as like a change in reasoning about the theory. But yeah, enriching in stuff that's like categories reifies the operational semantics by incorporating rewrites between terms. And then what we proved is that Cartesian functors between enriching categories induce this change of method between categories of models. So we'd like to thank Mike Stay and Greg Meredith for letting us build on their ideas. They had drafted a kind of a similar paper and acknowledged the support of Pyrofix and our chain. All right, thank you.
Next question. Any questions for Christian?
You restricted to products, the arities. Is there a reason for that? And if it's not the same question, does anything break if you use more general arities like binary powers?
So that is a more general theorem that I definitely want to prove. Just for our cases, we didn't need any theories at the time that were that involved generalized arities, but that's something that I definitely want to look at because, like John Power does a lot of really interesting stuff with generalized arities relating to these computational effects that you were mentioning. So yeah, I was talking with Rory. So we were using Lucius Shinwright's framework for parameterizing a theory by a system of arities. And so I was talking with him at the CT, and hopefully we'll talk about proving the general theorem so that we're not having to make this restriction. Yeah, thanks.
Chris, what was the name you said?
Rory Lucius Shinwright. It's yeah, monads and theories for a system of arities. Yeah, yeah.
So the product of two one-dimensional symmetric sets need not be one-dimensional. Is this a problem?
Oh yeah, that's a good point. Yes. So we haven't written down this this other perspective yet, but there's definitely some way that it'll work. The main problem with reflexive graphs is that they don't know that the reflexive loops are supposed to become the identities. So you can add simplicial sets know about their degeneracies. Yeah.
I'm more confident that it will work than you sound right now. Where we had been using graphs, we should have just said simplicial sets everywhere. That sounds a little scary because they have all these higher dimensional things. But you could, but the simplicial set enriched theories that you start out studying would be ones with only only non-degenerate zero simplices and one simplicity. So they would see the.
Yeah.
So there's a functor from graphs into simplicial sets, and we're only interested in that portion of the category of simplicial sets at first. But that portion is not closed under
Yeah.
five, so you get the whole
Yeah.
thing.
Yeah, and so the realization of a simplicial set preserves products, and it's going to collapse all that higher dimensional information down to a category. So, yep. Yep. Oh, sorry.
So yes.
So if I said the framework is very general,
Mhm.
have you thought about properties of rewriting systems that people care about, like confluence, normalization?
Yes. So far we're not sure how this could elucidate those kind of things, but it's something that going the other way, you would need to learn about rewriting theory in order to start to prove nice things within the enriched theory. So here, in order to sufficiently call the free set part the denotational semantics, you would want termination and confluence so that you can pick a normal form for the connected component. But for what this can actually contribute going the other way, we're not sure yet. But, yeah.
So in the context of arities not to just being natural numbers, maybe one could add one early reference, Frederick Infant lecture notes 80.
Oh, what was it?